Beginning of Unit 3, and in Unit 3 we're going to continue learning about different derivative rules for other functions such as trig functions, exponentials, and logs, and we'll also learn about something called implicit differentiation. But in this video we're going to focus on learning target 3a, which is about the derivatives of all the trig functions. So we'll be able to take the derivative of sine, cosine, tangent, as well as secant, cosecant, and cotangent by the end of this video. We're also going to incorporate all those rules about derivatives that we had from the power rule, product rule, quotient rule, and most importantly, the chain rule in this video as well. So all trig functions, when I take a derivative, is a chain rule. Since a trig function is a composition of that trig function, so in this case sine, with the input, which in this case is going to be x. So all of our derivatives of trig functions have to involve a chain rule. And in some cases, like our first derivative here, where we're asked to take the derivative of sine of x with respect to x, now this chain rule is going to seem a little silly since our inside function here is just the x, and we know that the derivative of x is just 1. But it's important to keep that in mind as we make these problems a little bit more complicated. So the derivative of sine of x with respect to x is cosine of x times 1. So the derivative of sine is cosine. We kept the inside the same here using the chain rule, times the derivative of x is 1, which is why we're multiplying by 1 then. Now let's look at a more generic case when I have sine of u. So u could represent any function in terms of x that I want, and we're going to take the derivative of sine of u with respect to x. So the derivative of sine is still cosine. Sine here is our outside function, so I took its derivative first. I'm keeping the inside the same, so the u stays the same, times, I have to chain rule this, so I'll be multiplying by the derivative of the inside, which is u, with respect to x. So in general, if I'm taking the derivative of sine of something, it will be cosine of that something, so that u, times the derivative of that something with respect to x. Let's look at a couple examples here. So I did forget to label these in your notes, so please do add y equals to all of these since I need to have the function have a name. And we're asked to differentiate the following functions. That means that I want to find the derivative. So on part A, we're given the function y equals sine of 3x, and I want to differentiate that function. So I'm going to find what y prime, or the derivative of y, is equal to. Well, here we have a chain rule, since we have a composition of functions. I have sine as my outside function and 3x as my innermost function. The derivative of sine is cosine. Keep the inside the same, so the 3x stays the same, times the derivative of the 3x would be times 3. So we'll see as we go throughout this section that we are using a chain rule on every single one of these, since all trig functions have an input which could potentially be a more complicated function. Let's look at example B. So in example B, we're given the function y equals sine of 4 times x to the 5th, and we want to differentiate that. So I want to find either y prime, or maybe this time I'll call it dy over dx. Remember those notations of y prime and dy over dx mean the same thing, and they are interchangeable. Again, here I'm going to have to use a chain rule. I have sine as my outside function. Derivative of sine is cosine. Keep the inside the same, so the 4x to the 5th stays the same, times the derivative of the inside would be the derivative of 4x to the 5th. I could use a power rule to take that derivative, and I would get 20x to the 4th. Hey, why don't you guys pause the video and do example C on your own first. So in example C, we have the function y equals sine of 3x squared plus 10x. And we're wanting to differentiate that function or find the derivative. I'm going to use dy over dx again to represent the derivative. I could use y prime. Those notations are interchangeable. My outside function here is sine. Derivative of sine is cosine. Keep the inside the same. Times, now the derivative of the inside function, I have two pieces here, and since they're added together, I can take their derivatives term by term. So the derivative of 3x squared is going to be 6x, plus the derivative of 10x will be 10. One thing that's different about C than A and B had was, since I had a sum of two functions as my innermost function, it is absolutely necessary that I have these parentheses around the derivative of the inside, since I want the entire 6x plus 10 to be multiplied to the cosine of 3x squared plus 10x. So make sure that we really do have those parentheses there, versus on example B, I really didn't need to put the parentheses since I just have one term that I'm multiplying there. The other thing that you guys will probably start to do out of habit is we usually put the coefficient in front. So in example A, for instance, we could rewrite this as 3 times cosine of 3x. And out of habit, you might start doing that. That is perfectly fine because multiplication is commutative, so the way in which I write that product does not change it. Okay, let's look at example D. So example D says y equals negative 3 times sine of 5x to the negative second. Why don't you guys pause the video and differentiate that function in example D? So to find our derivative here, I'm going to call it y prime. I could also call it dy over dx. Now I have a scalar here, this negative 3, that's a coefficient that's multiplied to the sine. We know from using in our past unit of unit 2 that any coefficients or scalars don't change the derivatives, they just go along for the ride there. If this was a negative 3x, I'd have to worry about a product rule then, since I have a product of two functions. But negative 3 itself is just a coefficient, so it's going along for the ride. For the sine of 5x to the negative 2, we do have a chain rule here. Outside function is sine, so we'll take the derivative of sine, which is cosine, keep the inside the same, times the derivative of the inside here, I can use a power rule on, and I'd get negative 10x to the negative third since we're subtracting 1 from there. It's important that we do want to have these parentheses here. Otherwise, that negative 10 might look like a subtraction sign instead, and we want to make it clear that we are multiplying this negative 10x to the negative third to that negative 3 cosine of 5x to the negative second. Now, as always, if this is a free response, you do not need to be simplifying your answers, but on a multiple choice, you would need your answer to match. So if we were to rewrite this, we could multiply the negative 3 and the negative 10, and we could also rewrite the negative exponents into the denominator. So if we were to rewrite this, negative 3 times negative 10 would give me 30. I would still have cosine, but instead of 5x to the negative 2, I could write that as 5 over x to the positive 2. All inside the cosine, divided by the x to the third if I wanted to just rewrite that. So those two lines are equivalent if you want to kind of combine coefficients and rewrite without any negative exponents, we could. Let's look at the derivatives of cosine. So the derivative of cosine, again, I'm going to have a composition here. Derivative of cosine itself is negative sine. Keep the inside the same, technically, times the derivative of the inside, which is that derivative of x, so I get the 1 there. Now this looks really silly to write the 1 since multiplying 1 by 1 doesn't change anything, but it's important to keep in mind that we always have a composition when we're taking a derivative of a trig function, so we want to make sure we're using the chain rule. If we generalize this a little bit more and we take the derivative of cosine of u with respect to x, again, u is representing any kind of function in terms of x that we might have. So we can use our chain rule here. Derivative of cosine is negative sine. We'll keep the inside the same times the derivative of u with respect to x. Since we don't know what u is, that would just be equal to du over dx, since this represents the derivative of u with respect to x. And that's just reminding us that we always need to be worried about that chain rule there. Let's look at some cosine examples now. Again, I'm sorry I forgot the y equals in your typed out notes, so please do add those there. We want to make sure we have a name for that function so we have a way to refer to its derivative. So in example A, it says we have y equals cosine of negative 4x, and we're asked to take the derivative or differentiate this function again. Well, we're going to keep using that chain rule. So I have cosine of negative 4x, so my outside function is cosine. So if I want to find the derivative here, dy over dx, that would be equal to negative sine. Since the derivative of cosine is negative sine, keep the inside the same, so the negative 4x stays the same, times the derivative of that inside would be negative 4. And we could multiply the negative 1 coefficient and the negative 4 coefficient and rewrite this as positive 4 sine of negative 4x as well. Let's look at example B. So in example B, we have y equals 3 times cosine of x squared. We're asked to differentiate or find the derivative. I'm going to use y prime this time for our notation. That 3 is just a coefficient on there, so it's going to go along for the ride. So I'll end up with 3 times derivative of cosine is negative sine. Keep the inside the same since we're using a chain rule, times the derivative of the inside function would be the derivative of x squared, which would give us 2x. Close all those parentheses. Now, if we were to combine some of our like terms here, I think I can fit it underneath. We have a 3 times a negative 1 times a positive 2, so we'd end up with negative 6x sine of x squared. So although there is absolutely no reason to rewrite these if it is a free response, I do want to make you guys aware of how you could kind of rewrite these and simplify them down if this was a multiple choice problem and you had to have your answer match. Let's look at example C. So in example C, we have y equals cosine of 4x plus 12. Why don't you guys pause the video and find the derivative for the function in example C. So let's check our derivative. I'm going to call it y prime. I could also call it dy over dx. I have cosine of 4x plus 12. I have a composition here, so to take the derivative, I'll be using a chain rule. My outside function is cosine. Derivative of cosine is negative sine. Keep the inside the same, times the derivative of the inside function would just be 4, since the 12 is a constant and the derivative of a constant is always 0. Well, let's look at example D. So in example D, we have y equals cosine of sine of x. So we have a composition here of quite a few functions. We have cosine as our outermost function. Then I have sine of x as the inner function to cosine, but sine of x itself is a composition as well. Why don't you guys pause the video and find your derivative there, and then we'll check it together. So let's check our derivative for example D. So I have a composition. I'm going to start with my outermost function, which is cosine. Derivative of cosine is negative sine. Keep the inside the same, since I'm using the chain rule. So the sine of x all stays the same, times, now I need to take the derivative of the inside function, which is the sine of x. I know the derivative of sine is cosine. Keep that inside function the same, which is an x. Technically, times 1 because of the derivative of this x inside the original sine function. So if I have a composition of trig functions with another input inside of a trig function, we will end up with this kind of double chain rule here. And in this case, yes, the innermost function of x, that derivative is just 1, but in case it wasn't just x, we would want to worry about how this could change overall then. All right, let's look at some examples where we put these rules together. So we're going to use both of our derivatives that we have so far. We'll use the fact that the derivative of sine is cosine, and the derivative of cosine is negative sine. We're going to use these to answer questions 3 through 8. So let's look at example 3. In all of these, they say to differentiate the following, but not to simplify our answers. And the reason that is it's a free response. I don't need to take the time to simplify my answer. And 2, when you're first starting out, you do want to leave stuff unsimplified. So as you're checking work, you can see if you made an error with one of the derivative rules or if it was more of a computational error. So let's look at example 3. We have f of x equals 3x times sine of 4x squared. What rule or rules do you guys think we're going to have to use to find our derivative on 3? So to find our f prime of x. Well, we're going to have to use quite a few. The first one I notice is I will have to use a product rule since I have 3x times sine of 4x squared. So I'll definitely be using a product rule. Let's start with that derivative. So the product rule says I take the derivative of the first function. So I'll take the derivative of 3x. That will just be 3. Keep the second function the same. So I'll rewrite sine of 4x squared. Plus, now I keep the first function the same. So I rewrite 3x. Times, now I have to take the derivative of sine of 4x squared. Well, that's going to involve a chain rule, and we have also already used a power rule as well. So first we have a product rule. Since I have 3x times sine of 4x squared. To take the derivative of 3x, I had to use a power rule. And to take the derivative of sine of 4x squared, I'm going to have to use a chain rule and a power rule. So here we have a composition. Sine is our outermost function. Derivative of sine is cosine. Keep the inside the same, so the 4x squared stays, times the derivative of the inside function. To take the derivative of 4x squared, we would power rule it and we would get 8x. And that will be our entire derivative of our original function f of x. So it's important that we remember that product rule in there because I have two separate functions here. I have 3x times sine of 4x squared. Okay, let's look at example 4. So in example 4, we have y equals sine of 3x times cosine of 5x. What rule or rules do you guys think we'll have to use to take the derivative for our function in example 4? So to find our derivative in example 4, again, we're going to need all three of those rules that we used actually in example 3. I have a product of two functions, so I definitely need to use the product rule. And then to take the derivative of each one of these individually, I'm going to need a chain rule with a power rule. So let's start with our first function here. Our first function is sine of 3x. I can take that derivative. Derivative of sine is cosine, so I'll have cosine of, keep the inside the same, so the 3x stays, times the derivative of the inside there is 3. Now I rewrite my second function, so times cosine of 5x stays the same, plus now I rewrite the first function, so sine of 3x stays the same, times now I can take the derivative of the second function. Derivative of cosine is negative sine. Keep the inside the same, so the 5x stays, times the derivative of 5x would give me 5. So we end up with definitely a large mess here of cosines times other cosines plus sines times other sines. We want to make sure we're understanding where each one of these pieces is coming from. So this first cosine of 3x times 3 is coming from the derivative of sine of 3x. Then I kept the second guy the same, so cosine of 5x stayed the same, plus now I keep the first function the same, sine of 3x, times this whole last piece is coming from the derivative of cosine of 5x. And that derivative again is a chain rule. Derivative of cosine is negative sine. We kept the 5x the same since that's the inside function, times the derivative of the inside function is 5. So we ultimately had that product rule with a chain and power rule on each other individual derivative that we had to take. Let's look at example 5 and 6. So in example 5 here, we have y equals sine of negative 2x over 4x cubed. Now there's a couple ways that we can do this. As it stands right now, I would need to use a quotient rule, or I could rewrite this as 4x to the third all to the negative first, and I could change it into a product and another chain rule. I want us to leave it as a fraction so we get practice with the quotient rule. And so let's start by taking our derivative here using our quotient rule. So our derivative for this guy, the quotient rule tells me that I have the bottom function, so the 4x cubed, times the derivative of the top function will be a chain rule with a power rule too. So on top I have sine of negative 2x. The derivative of that will be cosine of negative 2x times negative 2. Since I took the derivative of sine as cosine, kept the inside the same, times the derivative of the inside is that negative 2. Minus, now I rewrite the top function, times the derivative of the bottom function is a power rule, and that will give us a 12x squared. All of that is over our bottom function of 4x cubed, all to the second power. So we've got to be careful when we're using the product rule and the quotient rule in these, and just make sure we're taking it and making sure every piece lines up. And again, there is no need to simplify our answers here. We do not want to take the time to do that. Hey, why don't you guys pause the video and do example 6 on your own first and find the derivative of this function f of x. So let's check our derivative in example 6. So our function here is 5 minus 2x to the negative third times cosine of 7x squared. This is definitely going to be a product rule since I have a product of two functions. This first function in parentheses times that cosine of 7x squared. So using the product rule, it says I take the derivative of the first function. So derivative of 5 is going to drop to 0. Derivative of negative 2x to the negative third will give me a positive 6x to the negative fourth, since I have that double negative there, times, keep the second function the same, so cosine of 7x squared gets rewritten, plus, now I keep the first function the same, of the 5 minus 2x to the negative third, times the derivative of our second function will be a chain rule. We've also used a power rule as well already, and we'll use it again. But to take the derivative of cosine of 7x squared, I have a chain rule. Cosine is our outermost function. Derivative of cosine is negative sine. Keep the inside the same. Times the derivative of the inside there is going to be 14x. Just make sure we close all of our parentheses. So we've had our product rule of the derivative of the first function right here. Keep the second function the same, plus keep the first function the same, times this whole thing in parentheses there is the derivative of the cosine of 7x squared. So we can see with these trig functions, because since they all involve a chain rule, our derivatives are going to get very lengthy here because just chain rules expand the function quite a bit. Okay, we have two more examples until we move on to the derivative of tangent. Let's look at 7. So in example 7, we have y equals sine squared of 9x. So this will involve a chain rule because I have a trig function here. But what do you guys think the outermost function is? Because I have three functions going on right now. I have the sine, I have the squared, and I have the 9x. What do you think the outermost function is? Well, as it stands right now, it's really hard to think about what the outermost function is, and I want us to do a little review on the side over here. So in trig, we learned that we can square trig functions. So if I take sine of x and I square that whole thing, that would be equal to rewriting this as sine squared of x. This is really just kind of the lazy mathematician approach so that we don't have a bunch of parentheses that we're writing. Now this is helpful, so it's less to write down, but in terms of derivatives, it's actually helpful to expand this back out. So I'm going to have us expand out what sine squared of 9x means. So what that really means is I have sine of 9x, and then I square that entire trig function. So I'm not just squaring the sine, I'm not just squaring the 9x, I'm squaring the entire sine of 9x. This makes it a lot easier to identify what the outermost function is. So our outermost function is going to be that squared power. And the reason I need to know that is because we're going to actually do a double chain rule here. So the squared is my outermost function. Then I have of sine of 9x, but in that I have sine as kind of my middle function and 9x as my innermost function. So let's look at our derivative here. So to find our y prime, I'll take the derivative of the outer function first, which will be the squared. So the 2 comes down, keep the inside the same. All now technically to the first power times the derivative of the inside function. Well, the derivative of sine is cosine. Keep the inside of that the same, so the 9x stays the same, times the derivative of the innermost function would be that 9. And of course, this first power up here, we do not normally write since it's implied that if I don't have an exponent there, it's to the first power. Also with derivatives, primes and first power start to look really similar, so I'm going to have us take that off. So again, just to reiterate this, anytime you see a trig function that's like sine squared of 9x or sine cubed of 9x or cosine to the fifth of 10x, take the time to rewrite it with pulling the power out using that definition that we have from trig, that really taking sine of x and squaring that is the same thing as writing sine squared of x. but this top version up here is a lot more helpful in terms of when I'm taking a derivative, so I can really see that my outermost function there is the second power, and that my inner function is that sine of 9x. So we did use that double chain rule there. We also had to use a power rule as well, if I'm keeping track on the side. Let's look at example 8. So example 8 says f of x equals cosine of 4x plus 5 to the third. So this one's different than example 7. And the difference here is that that third power is only raising the 4x plus 5. It is not being applied to the cosine. In fact, it's actually inside the cosine. So what do you guys think here? What do you think is the outermost function? The cosine, the third power, or the 4x plus 5? So in this case, the cosine is my outermost function. So when I go to find f prime of x, my derivative here, I'll start with the derivative of cosine. That's negative sine. Keep the inside the same. So I'm going to rewrite 4x plus 5 to the third. Times, now I have to use the chain rule again to take the derivative of 4x plus 5 to the third. Now this derivative, the 3 is now my outermost power, so the 3 comes down, keep the inside the same, so 4x plus 5 to now the second, times the derivative of the inside there would be 4. We can close all those parentheses. Just to clean that up, that was a parenthesis. That was a 4x and the parenthesis. So we've got to be very careful here with what is our outermost function every time we're taking a chain rule. So in this case, cosine is the outermost function since that cube is inside these parentheses. And I can make these parentheses a little bit bigger for us to see. So we have these parentheses here. The cube power is inside that, so cosine is our outermost function. But again, we did use that chain rule twice, and we had to use a power rule as well a couple times. So we can see how even with just knowing how to take the derivative of sine and cosine, we can get lots of varieties in these examples since we still have our power, product, quotient, and chain rule from our last unit. Let's look at the derivative of tangent. Switch, there we go to purple. So the derivative of tangent, again, this is going to be a composition of functions here since I have tangent of x. So my derivative will involve a chain rule. Derivative of tangent is equal to secant squared of, keep the inside the same, so the x times the derivative of the inside function is the 1. So the derivative of tangent is secant squared, and if we were to rewrite that, that's secant of x, the entire thing squared. So in general, the derivative of tangent of u with respect to x will be secant squared of that function u times the derivative of u with respect to x. So again, this u is just a placeholder for whatever type of function I want to substitute in there. So I have this chain rule piece of the derivative of u with respect to x, which just represents the derivative of that inside function. Let's look at some examples. So here we have, in part A, it says differentiate the following. Our first function says y equals tangent of 3x squared. So we're going to find y prime or dy over dx, doesn't matter what we call it, both of those mean the derivative. I have a composition, tangent is my outside function, 3x squared is my innermost function. Derivative of tangent is secant squared. Keep the inside the same, so the 3x stays the same, times the derivative of the inside there would be a 6x by using the power rule. We can do the same thing in example B. So in example B, we have f of x equals tangent of 5x cubed minus 10x plus 4, and we're going to find our derivative, or f prime of x. I have a composition, tangent's my outermost function, derivative of tangent is secant squared. Keep the inside the same, so the entire cubic function gets rewritten as the input to secant squared, times the derivative of that inside function uses a power rule to get 15x squared minus 10. Let's look at example C. So in example C, we have y equals 1 over tangent of x. Now I could use a quotient rule on here, but I'm going to rewrite this so that we remember this trick from unit 2. So I can move the denominator up to the numerator by writing it as tangent of x all to the negative first power. And then the 1 that's a coefficient is just 1 times that. So really 1 times anything is not changing it. We're just looking at tangent of x all to the negative first. This will help us just continue practicing that chain rule. So here I actually have a double chain rule. My outermost function is the -1 exponent. Then tangent of x is my inner function. So to find dy over dx, or y prime, since I'm finding the derivative, start with the derivative of the negative first power. I'll power rule that and I'll get -1 times, keep the inside the same, so tangent of x to now the negative second, since I subtract 1, times the derivative of the inside. Well, the derivative of tangent of x would be secant squared of x times 1 from that second chain rule there. And let's look at our last example on page 77. So part D says f of x equals tangent of 7x. Why don't you guys pause the video and find f prime of x on your own first, and then we'll check that together. So to take the derivative of tangent of 7x, I'll chain rule it. Derivative of tangent is secant squared. Keep the inside function the same, so 7x stays the same, times the derivative of that inside function is going to be 7, since I have a power rule there. Okay, now let's look at our other trig functions that we have. So we are going to do some more examples where we put these all together, but I want us to have enough kind of new derivatives that we know how to take. So we're going to look at the derivatives of cotangent, secant, and cosecant up next. Oops. Whoa, sorry. There we go. Okay, so let's start with cotangent. So remember, COT is representing our cotangent function. By definition, cotangent is 1 over tangent. So we could get the derivative. We actually found it up above in part C when we took the derivative of 1 over tangent. But if we were to simplify that answer down, the derivative of cotangent is equal to negative cosecant squared of x times that 1 from the chain rule. So in general, the derivative of cotangent of u is equal to negative cosecant squared of u, cosecant squared of u, times the derivative of u with respect to x. And that derivative of u with respect to x is just representing the derivative of your innermost function there, which is u. So let's look at some examples to go with this. So in example 10, we have y equals cotangent of 8x to the negative first. So to find our y prime here, I have a composition, so I'll start with the derivative of the outermost function. Derivative of cotangent is negative cosecant squared. Keep the inside the same. So the 8x to the negative first stays the same, times the derivative of the inside there would be negative 8x to the negative second. That would be our derivative for the function in example 10. Now example 11 says f of x equals cotangent of 2x to the 6. Why don't you guys pause the video and find our derivative for example 11. So to check this derivative, we do have a chain rule. Outermost function is cotangent. Derivative of cotangent is negative cosecant squared. Keep the inside the same, times the derivative of that inside function is going to be 12x to the 5th by using the power rule. Okay, let's look at the derivative of secant. So remember, secant is 1 over cosine, so we could get the derivative that way and simplify it down. If you were to do that, we would find out that the derivative of secant is equal to secant of x times tangent of x times 1. So this is a little different here. So the derivative of secant is secant tangent. Both of these have an input of x here because I had an original input of x here. So if I would have had a different input, let's say 2x, then both of these would have had a 2x here, and then I would have multiplied by 2 since the derivative of that 2x would be a 2 instead of the 1 here. So when we do this in general and take the derivative of secant of u with respect to x, we're going to get secant of u times tangent of u times the derivative of u with respect to x. So although our innermost function is going into 2 places here in our derivative, I only multiply by the derivative of the inside function once, because this is coming from the chain rule versus secant tangent is coming from the fact that the derivative of secant, by definition, is secant of that times tangent of that. So secant is definitely a little bit different there since I get a multiplication of trig functions as my derivative. So let's see this in action with example 12. So example 12 says y equals secant of negative 3x, and we want to find our derivative. So our dy over dx. Our outside function here is secant. Derivative of secant is secant of something times tangent of that same something. So I'm going to get secant of negative 3x times tangent of negative 3x times the derivative of the inside function. Our inside function is negative 3x. Derivative of that would be negative 3. Let's look at example 13 here. So we have f of x equals secant of x squared. Why don't you guys pause the video and find f prime of x. Find that derivative. So to check this, I have a composition. Derivative of secant is secant times tangent. For both of those, I input my inner function since my inside function stays the same, so I'll have an x squared for both of those, times the derivative of the inside function would be a 2x from the derivative of x squared. Okay, one last trig function. Our last one is the derivative of cosecant. Now, cosecant is 1 over sine, by definition, just in case we need that trig review. The derivative of cosecant is equal to negative cosecant of x times cotangent, times cotangent of x, technically times the 1 from the chain rule. So both secant and cosecant kind of have this product of trig functions as its derivative. So just like before, since x was my input, both negative cosecant and cotangent both have an x as an input there, and then 1 is coming from the derivative of that x. So in general, the derivative of cosecant of u with respect to x would be equal to negative cosecant of u, cotangent of u, and those are multiplied, times the derivative of the inside function, which is the derivative of u with respect to x. Let's look at a couple examples for those. So our first function, we have f of x equals cosecant of 7 over x. I'm going to have us go ahead and rewrite 7 over x to avoid a quotient rule as when I take the derivative of the inside. So I can rewrite that as 7 times x to the negative first. Only the x is being raised to the negative first, not the 7, since only the x was in the denominator to begin with. The reason I did that was just to avoid a quotient rule when I take the derivative of the inside. But if you wanted to, you could leave it and use a quotient rule to take the derivative of the inside. I have a composition here. Derivative of cosecant we know is negative cosecant of that thing times cotangent of it. My inside function here is 7x to the negative first. So I get 7x to the negative first as the input for both of those trig functions. Times the derivative of 7x to the negative first. I can power rule that and I'll get negative 7x to the negative second. And that will be our derivative for 14. 15 is our last example here with just cosecant, and it says y equals cosecant of 4x squared minus 3. Why don't you guys pause the video and find our derivative here, or our dy over dx. Okay, let's check 15. We have a composition of functions. Cosecant is my outermost function. Derivative of cosecant is negative cosecant times cotangent. Both of those get the same input, which is the 4x squared minus 3. From the original function times the derivative of that 4x squared minus 3 would be an 8x. So we've now taken the derivative of all 6 trig functions: sine, cosine, tangent, cotangent, secant, and cosecant. Now, yes, all 6 are fair game. Definitely sine, cosine, and tangent come up a lot. Secant, I would say, is the one that comes up the most after that, but cotangent and cosecant are still fair game. And although we don't have any new rules here, in the sense that we're still using our chain rule, maybe a product or a quotient rule, and sometimes a power rule as well, we do want to have these derivatives of trig functions memorize. So I do want to know right off the bat that the derivative of sine is cosine. We should know that the derivative of cosine is negative sine. We should know that the derivative of tangent is secant squared. We should know that the derivative of cotangent is negative cosecant squared. The derivative of secant is secant times tangent, and that the derivative of cosecant is negative cosecant cotangent. One thing I do have at the bottom of the page here is it's a little trick to help you remember these. This is not why I have negative signs, but one thing that they happen to have in common is that all trig functions that start with a c, so cosine, cotangent, and cosecant, all happen to have a negative sign in their derivative. Now that's not why they have a negative sign in their derivative, but it just so happens that all three trig functions that start with a c have a negative sign. So I know one of those things that we can easily forget is that negative or positive sign, so this can just be a little trick to help you remember that. Okay, let's look at a couple examples where we put these together. So in example 16 here, we have, or for all of these, it's asking us to differentiate the following and not simplify our answers. So in example 16, we have y equals tangent of x squared minus 3x times sine of 4x minus 19. There's a lot going on here. So I have three functions. I have tangent of x squared minus 3x times this sine function. I will have to use a product rule for the second half since I have 3x times the sine function, but the tangent of x squared is not going to be part of that product rule since it's tangent of x squared minus the product. So when I go to take my derivative here, we'll start with the derivative of tangent of x squared. Derivative of tangent is secant squared. Keep the inside the same, so the x squared stays the same, times the derivative of that inside function will be 2x. That's just coming from the derivative of tangent of x squared. Now for the product rule, I got to be careful with this. I have a negative 3x as my first function times the sine function. The product rule tells me that I take the derivative of the first function, so the derivative of negative 3x would be negative 3. Keep the second function the same, so the sine function just gets rewritten, plus technically the first function rewritten, which is negative 3x, times the derivative of the second function. Now the derivative of sine of 4x minus 19 will involve a chain rule. So derivative of sine is cosine, keep the inside function the same there, times the derivative of the inside function there would be 4. And we're leaving these all unsimplified. So just make sure if I have a product of two functions that we are using the product rule correctly for those. Okay, let's look at example 17. So in example 17, we have y equals cosecant of negative 8x plus x cubed times 5x plus 12 all to the fourth. Now what rule or rules do you guys think we're going to have to use here for example 17? So the first thing I notice is I have a product. I will be using the product rule. I will also have to use the chain rule on each of these as well as some power rules. So let's start writing this out. My first function here is the cosecant. Derivative of cosecant is equal to negative cosecant times cotangent. And my inputs for both of these will be the same. The original negative 8x plus x cubed, times, that was supposed to be a 3, times, I'm going to have to write it above since the page number is there, the derivative of the inside. Derivative of negative 8x plus x cubed will be negative 8 plus 3x squared. So that's all being multiplied. Now keep the second function the same. So 5x plus 12 to the fourth stays the same. So there's the first half of the product rule. Now plus keep the first function the same. So I'm going to rewrite the cosecant mess. Times, now the derivative of the second function will involve another chain rule. The fourth power is your outermost function, so the 4 comes down. Keep the 5x plus 12 the same to the third now, times the derivative of that inside function is going to be equal to 5. So lots going on in example 17 since I have a product of two functions, and those each involve a chain rule when I take their derivatives individually. Let's look at some more examples here. so in example 18, we have f of x equals cosine of tangent of 4x. What rule or rules do you guys think we'll have to use in example 18? So in example 18, I'm going to have to use the chain rule twice and a power rule as well when we take the derivative of 4x. So here, my outermost function is the cosine, and then tangent of 4x is my inside function. So let's start with the derivative of cosine. Derivative of cosine is negative sine. Keep the inside the same, so the tangent of 4x stays the same, times the derivative of the inside now. I have tangent of 4x, so tangent is now my outside function. Derivative of tangent is secant squared. Keep the 4x the same, times the derivative of 4x would be 4 there. So we have a double chain rule here. I have cosine of tangent of 4x, so I have to first do the derivative of cosine, which is negative sine. Keep that whole inside function the same, so tangent of 4x. Now I'm just taking the derivative of tangent of 4x. That also involves a chain rule. Derivative of tangent is secant squared. Keep the 4x the same, times the derivative of 4x is 4. Okay, let's look at example 19. So in example 19, we have y equals x squared times cotangent of 7x minus 14. What do you guys think? What rule or rules will we have to use in example 19? So in example 19, I'm going to use a chain rule, but first I need to use the product rule since I have x squared times cotangent. So let's start writing out our derivative. I'm going to call it dy over dx, or I could call it y prime. I have a product of two functions here. So the derivative of the first function is going to be 2x. Keep the second function the same. So that cotangent of 7x minus 14. Plus, keep my first function the same, so the x squared stays the same. Times, now the derivative of cotangent will involve a chain rule here. Derivative of cotangent is negative cosecant squared. Keep the inside the same. Times the derivative of that inside will be that power rule, which will just be 7. So lots can go on in all of these now that we know how to take the derivatives of any trig functions and we have all those rules from Unit 2. Let's look at example 20. We have f of x equals tangent to the fifth of 7x plus the square root of x. That's got a lot going on. What rule or rules do you guys think we're going to have to use on example 20? So in example 20 here, we're going to have to use the chain rule twice and a power rule as well. So our outermost function here is actually that fifth power. I'm going to want to go ahead and rewrite this. So this is tangent to the fifth of this is the same thing as tangent of 7x plus, I'm going to rewrite the square root as well as x to the 1/2, all raised to the fifth power. So remember that power on that trig function is not just on the trig function, it's on the entire tangent of the 7x plus the square root. So when I rewrite that now, it's easier to see that my fifth power is my outermost function. So we're going to start with the derivative of the outermost function. This will be a double chain rule. So the 5 comes down, keep the inside the same, all to the fourth power now by taking the derivative of that fifth power, times the derivative of my inside. Derivative of tangent is secant squared. Keep that inside function the same, times the derivative of that inside function. So I'm now taking the derivative of 7x plus x to the 1/2 will be 7 plus 1/2 x to the negative 1/2. And we've got to be really careful with the parentheses here. So all of these are being multiplied. It is key that we have parentheses around the 7 plus 1/2 times x to the negative 1/2, since that whole thing is the derivative of this inside function. So that needs to get multiplied to the secant squared of that mess. I also want to make sure that when I have trig functions, I should be putting their inputs in parentheses so it's very clear what is the input there. If I didn't have parentheses around it, especially in this case where I have a sum of two things, I would not have that entire input as the input to secant squared. Okay, we have two last examples. Why don't you guys pause the video and take the derivative for example 21, and then we'll check it together. Okay, let's check 21 together. So 21 says f of x equals cosine of 7x plus 2x, All of that is raised to the negative fourth power. So we've got some chain rules going on here. That negative fourth power is my outermost function. So the negative 4 comes down. Keep the inside the same. So cosine of 7x plus 2x all stays the same to now the negative fifth, since we're subtracting 1, times, now these parentheses are going to be necessary that I'm writing down, the derivative of the inside here. We have to be careful. When I take the derivative of cosine of 7x, that will involve a chain rule, but that is not going to involve a chain rule for just the derivative of 2x. And since cosine is being added to the 2x, I can do these derivatives individually. So the order in which I write these down, I've got to be careful. I'm going to start with the derivative of cosine of 7x. Derivative of cosine is negative sine. Keep the inside the same, so the 7x stays the same, times the 7. And that 7 has to get multiplied right away since it's only part of the derivative of cosine of 7x. Now plus the derivative of 2x there, using the power rule, is just 2. So there is a huge difference on if I put the times 7 right next to the sign or if I put the times 7 outside of these parentheses. It has to be attached to the negative sine of 7x since that's the portion that involves the chain rule. The 2x derivative has nothing to do with the cosine of 7x since those functions are being added together. So I take their derivatives separately, but they're all inside parentheses since the entire cosine of 7x plus 2x was my innermost or my inside function here. And our last example. So example 22 says 2x to the 6 minus x times secant of 8x. Again, why don't you guys pause the video and find your derivative for example 22. Okay, let's check example 22. So I will have to use a product rule, but the 2x to the 6 is not part of that product rule since it's being subtracted to this x times secant of 8x. So I'll start with the derivative of 2x to the 6. That will be 12x to the 5th by using the power rule. Now I have a product of two things. I have this negative x times this secant of 8x. So let's start with the derivative of the first guy. Will just be negative 1 times, keep the second function the same, so secant of 8x, plus my first function, which is negative x, times the derivative of secant of 8x will involve a chain rule. Derivative of secant is secant times tangent. Both of those get the input of 8x. Finishing off the chain rule, I multiply by the derivative of 8x, which would be 8. So here on this last example, we did have to worry about a product rule with the negative x times the secant of 8x. So we just got to be careful that we have that product rule there, but the 2x to the 6 has nothing to do with our product rule since it is just being added to that other piece. So in this video, we went through lots of examples with different trig functions. You should be able to take the derivatives of sine, cosine, tangent, cosecant, secant, and cotangent. So we want to make sure we have all 6 of those derivatives memorized, and we'll continue to practice this more in class tomorrow and incorporate more of these rules